Today, we're tackling something huge, maybe the biggest puzzle there is, the fundamental structure of the cosmos. We're going deep into the major conflicts in modern physics and the pretty radical ideas needed to maybe solve them. Specifically, we're looking at string theory. What does it force us to accept about reality itself?
It's definitely ambitious. Because as our sources lay out, the heart of the problem is this huge clash between the two main pillars of physics from the last century. You've got Einstein's general relativity, that's the physics of the big stuff, gravity, stars, galaxies, and then there's quantum mechanics, the physics of the ultra-small, atoms, particles. And to really get string theory, we first need to grasp why Einstein had to rewrite space and time. Only then can we see why string theory says, okay, now rewrite them again.
Right. So let's jump straight to that core conflict. What happens when you try and use both theories together, general relativity, or GR, and quantum mechanics, QM? Especially in extreme places, like inside a black hole singularity, where you have immense mass crushed down to basically zero size.
That's exactly where it all falls apart. The math doesn't just give a wrong answer. It completely breaks down. It yields infinities. You try to calculate something fundamental, like the energy fluctuations in empty space, using both GR and QM. And the answer isn't just big, it's infinite, which is, well, nonsense physically. It signals the framework just can't handle it. So for decades, the big question was, does the universe really operate on two different sets of laws? One for the large scale, one for the small. And they're incompatible.
Okay, that failure points us back to Einstein, because he actually solved an earlier major conflict. Before GR, Newton's gravity theory, well, it implied that gravity acted instantly, like the sun pulls on the Earth right now, but that totally contradicted Einstein's other theory, special relativity, which established the ultimate speed limit: nothing travels faster than light.
Exactly. Newton's action at a distance couldn't be right if special relativity was right. So Einstein, in 1915, came up with general relativity, and his solution was just stunning. Gravity isn't some force reaching across space. It is space, or rather space-time, bending and warping because of mass and energy. Space-time stops being just a passive stage. It becomes an active participant.
Ah, the famous analogy time, like putting a bowling ball on a stretched rubber sheet. The heavy ball makes a dent, a curve.
Precisely. That curve is gravity. And if something changes, say the bowling ball moves, ripples or disturbances travel outward through that sheet. And crucially, those ripples, gravitational waves, travel at the speed of light, 670 million miles per hour. Problem solved. It fits perfectly with special relativity.
But special relativity itself, SR, is still deeply weird for our everyday intuition. It's built on just two core ideas, right? One, the principle of relativity. All motion is relative. There's no absolute rest. And two, the constancy of the speed of light. No matter how fast you're moving, you always measure light speed as the same value. Always 670 million miles per hour.
And it's that second point, the unchangeable speed of light, that messes with everything we think we know about time and space. Think about muons. They're particles created high up in the atmosphere, and they zip down towards us at like 99.5% of light speed.
Yeah.
Now, from their own point of view, they live for a tiny fraction of a second, a standard lifespan.
Yeah.
But from our perspective down here in the lab, because they're moving so incredibly fast relative to us, their internal clocks appear to tick much, much slower.
So they seem to live longer, like 10 times longer, just because they're moving fast, which means time isn't this rigid universal metronome. It stretches and squeezes.
It's entirely relative. And this flexibility, it also kills the idea of universal now. Simultaneity goes out the window. If you and I are moving relative to each other, events I see happening at the exact same instant, you might see happening one after the other. There's no absolute agreement on it at the same time.
Which leads to this profound shift in thinking, thanks to Hermann Minkowski. He said, basically, time is just the fourth dimension. His big insight was that everything, absolutely everything, is always moving through this four-dimensional space-time, and always at one fixed speed, the speed of light.
Yeah, that's the really mind-bending part. Your motion budget is fixed at light speed, distributed across four dimensions, three space, one time. So if you're sitting still right now, relative to the Earth anyway, you're not moving much through space. So almost all your light speed motion is through the time dimension that's aging. But start moving fast through space, and you divert some of that motion budget away from the time dimension into the space dimensions. So your motion through time has to slow down. That's time dilation, fundamentally.
And the ultimate example, light itself. It travels at the maximum speed possible through space, which means it has used up its entire motion budget on spatial travel. There's nothing left for moving through time.
So light doesn't experience time. A photon is emitted, travels across the universe, and is absorbed. From its perspective, Zero time has passed. It doesn't age.
Okay. So Einstein gives us this smooth, curved, relative spacetime, but now we have to zoom way, way in to the quantum realm. If GR spacetime is smooth, what happens down at the scale of atoms and electrons where things get jumpy, probabilistic?
Right. You enter a world governed by quantum mechanics, QM, and as Richard Feynman famously said, I think I can safely say that nobody understands quantum mechanics because QM tells us our fundamental classical ideas just fail. Things like knowing exactly where a particle is and where it's going. Nope, can't do it. Particles are inherently fuzzy. Their properties are described by probabilities, not certainties, until you measure them.
It required a whole new way of thinking, starting with Max Planck, right? Around 1900, he was looking at the energy emitted by hot objects, like inside an oven. And the existing physics predicted something absurd.
Totally absurd. Classical physics said the oven should emit energy at all frequencies, and the hotter the frequency, the more energy. It led to this prediction of infinite energy coming out of the ultraviolet catastrophe. Clearly wrong. Planck made a radical guess. He said, what if energy isn't continuous? What if it comes in little packets, little lumps, quanta, like money you can't pay with fractions of a cent? The size of the energy packet, the quantum, is proportional to the frequency.
So for very high frequencies, the required energy lump is just too big for the oven to easily produce. It choked off the absurd infinite result. It made the math work, but it was seen as just a trick initially.
Until Einstein picked it up 5 years later. He used Planck's idea to explain the photoelectric effect, why light shining on metal can knock electrons off. Einstein argued Planck's quanta weren't just a calculation trick. Light itself is made of these particles, photons, packets of energy. And crucially, the energy of each photon depends on the light's frequency, its color, not its brightness. You need a photon with enough energy and a frequency to kick that electron out. More low-energy photons won't do it.
Okay, so energy comes in lumps, light comes in particles, but doesn't light also act like a wave? That leads to the double slit experiment, the ultimate quantum weirdness. You fire particles, like electrons, one at a time, towards a barrier with two slits in it.
Right. And you expect, common sense says, each electron goes through either slit A or slit B, like tiny bullets. You should just see two bands on the detector screen behind the slits.
Yeah.
That's not what happens. Even firing them one by one, slowly, over time they build up an interference pattern on the screen. That pattern, with multiple bands, is characteristic of waves passing through both slits at once and interfering with each other. It implies each single electron somehow went through both slits. It interfered with itself, which is just deeply bizarre. It defies our everyday logic about definite paths.
So we have these two incredibly successful theories, GR for the smooth cosmos, QM for the weird, jumpy micro world. But try to describe something where both are important, like the Big Bang or a black hole center, and boom, infinities. The theories clash violently. That's the core problem string theory tries to solve.
Exactly. String theory comes along, starting seriously in the mid-1980s, and proposes a really fundamental shift. It says, forget point particles. The basic constituents of reality aren't zero-dimensional dots. They're tiny, one-dimensional vibrating filaments. Strings.
Like infinitesimally small guitar strings or rubber bands, and that solves the problem.
Well, that's the core idea. The different ways these strings can vibrate, their different notes or resonant patterns correspond to everything we see. One vibration pattern looks like an electron, another looks like a quark, another a photon. And crucially, one specific vibration pattern corresponds precisely to the properties of the graviton, the hypothetical particle that carries the gravitational force. So for the first time, you potentially have a single framework where all particles and all forces, including gravity, emerge from one fundamental entity, the vibrating string. It unifies matter and forces.
Okay, that sounds incredibly elegant. Unification is the holy grail. But there's a catch, isn't there? A big one. It requires, as you said, completely revamping our picture of space and time again.
A very severe revamping. To make the mathematics work, to cancel out those problematic infinities that plague the point particle theories. String theory doesn't work in the familiar 3 spatial dimensions plus 1 time dimension. It requires extra spatial dimensions. Most versions need 9 space dimensions and 1 time dimension. So a 10-dimensional spacetime.
9 space dimensions. Okay,
Yeah.
That's hard to grasp. 3, we know, length, width, height. Where could the other 6 possibly be? How do we make that plausible?
The standard analogy is the garden hose. Imagine looking at a long garden hose from really far away. It just looks like a line, right? One-dimensional. You can only move along its length. But get closer, zoom in, and you see it has thickness. It has a second dimension, the circular girth that was hidden from view because it was small and curled up. String theory suggests something similar might be true for our universe. We have the 3 big dimensions we move around in, But at every point in that space, there could be 6 extra dimensions, curled up incredibly tightly, curled up into complex geometrical shapes called Calabi-Yau spaces, possibly as small as the Planck length itself. Too small for us to have ever noticed.
Okay, so tiny hidden dimensions, and the shape of those dimensions matters.
Immensely. But first, string theory changes geometry itself at those tiny scales. The smooth, continuous geometry of Einstein's GR, called Riemannian geometry, it turns out, is only an approximation. It breaks down at the Planck scale, about 10 to the minus 33 centimeters. String theory introduces what's called quantum geometry.
Quantum geometry, what does that entail?
One of the most mind-boggling aspects is something called T-duality. Think about one of those extra dimensions being curled up like a circle. A string, being an extended object, can do something a point particle can't. It can wrap around that circle. This is called a winding mode. Now, the math of string theory shows something absolutely bizarre. The physics in a universe where that circular dimension has a radius r is exactly identical to the physics in a universe where the dimension has a radius 1r measured in Planck units.
Wait, so a really, really tiny curled-up dimension gives the same physics as a really, really big one. That makes no sense classically.
None at all. It means there's a fundamental minimum size in the universe, related to the Planck length. If you try to squeeze a dimension smaller than this, the physics acts as if it's getting bigger again due to this r and 1r duality. You literally cannot probe distances smaller than the Planck length in string theory. The concept of smaller breaks down. It fundamentally rewrites the rules of geometry at short distances. And yes, the precise shape of those 6 curled-up Calabi-Yau dimensions is critical. Their geometry is thought to determine the fundamental constants of nature we observe, like the mass of the electron or the strength of electromagnetism.
And there's even more weirdness there, right? Mirror symmetry.
That's right. It turns out that sometimes 2 Calabi-Yau shapes that look completely different from a classical geometric perspective can, according to string theory, give rise to exactly the same physical laws in the large dimensions. They are physically indistinguishable, even though their geometries are different. It's another layer of quantum geometry fuzziness.
Wow. Okay, so we've gone from Einstein bending spacetime to quantum fuzziness, and now to vibrating strings in hidden dimensions where small can be the same as large. That's quite a journey. Where does this leave us? What's the path forward for string theory?
Well, we have this incredibly powerful mathematical framework. It seems to have the capacity to unify everything we know about fundamental physics. But testing it directly is fantastically difficult. To actually see a string, to probe its structure, you'd need energies that are orders of magnitude beyond anything conceivable with current technology. You'd essentially need a particle accelerator the size of a galaxy.
So direct proof is off the table for now. We need indirect evidence. What are the key predictions we might be able to test?
The most robust generic prediction that comes out of most string theories is supersymmetry. It's often called ACSY. Supersymmetry is a kind of symmetry that relates the 2 fundamental classes of particles, fermions, matter particles like electrons and quarks, and bosons, force carriers like photons. It predicts that every known particle should have a heavier superpartner particle with slightly different properties, specifically its spin. So the electron would have a selectron, the photon a photino, and so on. Finding these superpartners, these sparticles, at accelerators like the Large Hadron Collider would be huge. It wouldn't definitively prove string theory, but it would be extremely strong circumstantial evidence that its core mathematical structure is on the right track.
Okay, finding sparticles is the big experimental hope. Now, for our final provocative thought, let's push on this quantum geometry idea. You mentioned string theory allows the fabric of space to rip and repair topology change. And we know black holes evaporate via quantum effects, eventually becoming massless. At that point, a massless black hole could, in principle, transmute into just fundamental particles, maybe a photon, maybe a graviton, which are just
specific vibration patterns of the string. Yes, the endpoint could literally be a fundamental string excitation.
Right. So if the extreme conditions inside a black hole resemble the Big Bang in some ways, and if black holes can ultimately turn back into fundamental stuff, could black holes be, I don't know, seeds? Seeds for new universes? Does it suggest that maybe the laws of physics aren't just fixed and elegant, but maybe they've evolved? Like cosmic natural selection, where universes that are good at making black holes, which spawn new universes, become dominant? That's definitely something to chew on.